Today, we are putting on our detective hats. We're going beyond just standard troubleshooting and diving deep into the world of cloud network forensics. This is a place where the clues are buried in code and configs, and the crime scene itself is a virtual environment. So let's open the case file. And this really is the central mystery for any of us working in the cloud today, isn't it? I mean, the days of just SSHing into a box and running a quick ping or trace route, they're kind of fading. In these new abstracted cloud environments, our problems are hiding, and our tools have to be a whole lot smarter. So how do we find the culprit when our go-to methods are completely off the table? So here's what we've got on the docket. First, we'll take a look at the new toolkit every cloud detective needs. Then we'll investigate a couple of cases. We're going to hunt down an elusive ghost and then try to figure out a silent black box. We'll also solve a classic financial mystery, the case of the runaway network bill. And we'll wrap up by looking at what it really means to be a modern network troubleshooter. To solve these modern mysteries, you're going to need a modern toolkit. See, in the cloud, our investigations rely on platform-level intelligence. We're talking about tools that can analyze the entire network fabric itself without you ever having to log into a single server. All right, let's crack open our first case file. We're calling this one the Ghost. Here's the situation. You have a really strong feeling there's a malicious process running on your production servers. But it's smart. It only communicates every once in a while, which makes it incredibly hard to catch in the act. It's a ghost in the machine. Let's examine the scene. We've got a production app running on compute engine. We think there's something bad happening on the front-end servers. Our goal here isn't just to stop it. We need to capture all of its traffic for a full forensic analysis. We need that hard evidence. Okay, so our main surveillance tool for this job is going to be VPC Flow Logs. It's perfect for this. It captures metadata on IP flows going to and from our network interfaces. But, and this is a big but, there is one specific setting that will make or break this entire investigation. It's the difference between catching our ghost or letting it slip right through our fingers. And this right here is that critical choice, the sample rate. You could set it to 0.5, which grabs about half the packets. For general day-to-day monitoring, maybe that's okay. But for security, it's a massive gamble. If our malicious process only phones home for a few seconds every minute, we have a literal coin flips chance of missing it completely. The other option is a sample rate of 1.0. That captures everything. It's the guarantee. This analogy just hits the nail on the head. Would you ever install a security camera that only records for 30 seconds out of every minute? No way! A burglar is going to strike in that exact moment the camera is off. For forensics, a 50% sample rate is that faulty camera. So the bottom line is this. When your goal is forensic analysis, there is only one right answer. A sample rate of 1.0, 100%. Case closed. You guarantee you capture all the network traffic, and that gives you the complete, untampered evidence you absolutely need. Let's move on to our next case. We're calling this one the black box. This is a classic connectivity whodunit. You've got two services that are supposed to be talking, but one of them is just getting the silent treatment, and you have absolutely no way to look inside the box to see what's going wrong. So here's the situation. We've got two Google Kubernetes engine clusters, each in its own VPC. Cluster A is supposed to be able to reach cluster B, but nothing. You're pretty sure it's a network config problem, but here is the kicker. You are completely locked out. You have zero permissions to SSH or run commands on any of the nodes. And right there, we hit a brick wall. Our entire traditional toolkit, it's completely useless. We can't SSH in to run a ping. We can't trace route the path to see where the connection dies. Our hands are totally tied. So what's a modern detective to do? Well, you use a tool that doesn't even need to send a single packet. You use something called Reachability Analysis. This is the core idea behind Google's connectivity tests. It's basically a super powerful simulation. It models your entire setup, your VPCs, your firewall rules, your routes, and it mathematically figures out the exact path a packet would take and whether it would be allowed or denied at every single step. And this brings us to the ultimate question in pretty much any connectivity case, right? Where is the packet dropping? That's what we need to know. And because reachability analysis simulates the entire path, it can tell us with absolute certainty. And there it is. The simulation runs, and it comes back with a definitive result. The packet is being dropped by a specific firewall rule. In this case, deny all egress. No guesswork, no more tedious manual checks. Just a clear, actionable answer. Mystery solved. Okay, for our final case, our investigation is going to take a little bit of a different turn. We're not hunting a bad actor this time. We're following the money. This is the case of the mysteriously high network bill, where the real culprit is an inefficient configuration that's just bleeding your budget dry. Let's look at the evidence. We have a GKE cluster running a mobile game. Now, the players are all over the world, but the application itself is hosted in a single region. We'll say the UK. The problem is that data egress, data leaving the network, is costing a fortune. Our goal is to find the single most effective change we can make to slash that cost. Now, to solve this, we need to understand a key suspect: network tiers. With the premium tier, your users' traffic gets onto Google's awesome private network as fast as possible. This is great for global apps needing low latency everywhere, but you pay a higher price for that egress. Then there's the standard tier. This keeps traffic on the public internet longer, and it only enters Google's network close to your service region. It's perfect for regional apps, and you guessed it, comes with a much lower egress cost. Now, here's where a lot of detectives get led astray. They might start thinking about big architectural changes, like making the cluster private or setting up a new ingress. But those things solve different problems, usually stuff related to security or access control. They don't fundamentally change the pricing model for the data transfer itself. The tier fix is what directly targets the data path, and because of that, the egress cost. So, the solution is crystal clear. Since the application itself is regional, switching to the standard network tier aligns the cost model perfectly with the architecture. It's the most direct and effective fix for high egress costs in this particular scenario. Case closed. So, after going through these cases, what have we really learned? We've seen how to catch a ghost with total data capture, how to trace a path through a black box using simulation, and how to follow the money to solve high costs. All of this points to a really fundamental shift in our role as engineers. And honestly, this is the central idea of this whole explainer. The skills that make a great cloud network troubleshooter today are changing. It's becoming less about your muscle memory with command line tools and way more about your ability to understand and leverage the powerful, high-level intelligence that's built right into the cloud platform itself. Which leaves us with a final question to think about. As our network infrastructure becomes defined entirely by code and configuration, is the skill of the investigative detective, the person who analyzes the system as a whole, becoming more valuable than the hands-on mechanic who just fixes one component at a time? It's something to consider as you go out and solve your own cloud mysteries.